Hello everyone, welcome to Introduction to Geotechnical Engineering. My name is Jean-Louis Briaud. I'll write it here. So the last name is pronounced as if it was B-R-I-O, Briaud. Little bit of background, I was born, raised, educated in France. When I was 22, I got my bachelor's degree, and then I wasn't ready to get into an office and start doing calculations as an engineer. So I decided to go and do my master's and my PhD in Canada. And I met my wife there as well. We got married. And then I went to 1978. I came down to Texas A&M University, and I've been here ever since, going through the progression ladder. So this is Introduction to Geotechnical Engineering. I'll tell you in a minute a little bit about geotechnical engineering and also about geology, which is a very important topic in geotechnical engineering, but I wanted to go over the syllabus with you. So first thing, I want to make sure that you can reach me anytime you wish. So I want to give you my phone number. So at the office, it's 979-845-3795. And this is my cell phone, 979-777-1692. And I don't mind you calling me on my cell phone or even texting if you prefer. And email as well. And all this is on the syllabus, but I wanted to write it. So it's Briaud@tanu.edu. Okay. I want you to know that you have priority. Okay, so I have office hours Tuesdays from 12 to 3. That's the dedicated time. But really, my office hours are anytime. Okay, you can call me. I go to bed around 10:30, so get up early. But anytime you need me, just call me, text me, email me. I'll do my best to respond as soon as I can. All right. So this is what's on at the top of the syllabus. And the syllabus is uploaded on Howdy. So course description, you have this, prerequisite lectures. So the lectures are Monday, Wednesday from 8 to 8:50, but it's going to be remote learning, and we're taping the lectures, and we will distribute the videos before the lecture, so you can watch them. It's going to be on a shared folder on a Google Drive, again ahead of the lectures. And you'll be notified by email when each lecture becomes available. The textbook is this book here, Geotechnical Engineering, Unsaturated and Saturated Soil. It's written by Jean-Louis Briaud. Oh, that's me. It's a pretty good book. I'm a bit biased, obviously. All right, seriously. So, and the book is not, you know, if you're going to deal with geotechnical engineering in any fashion, you may not be a geotechnical engineer, but most of you will be civil engineers, and you will interact either as a structures, environmental, transportation. You're going to have to deal with the soil because everything we do is going to rest on the soil. So it's probably a good book to have on your shelf because it's very general. It covers a lot of different topics, not just what we'll see in in this introduction course, but many more things. So it's not a bad investment. It's not something you buy and then you throw out at the end of the course. At least I hope not. All right, so that's the book. The book, it's 1,000 pages. It's got about 400 problems and solutions. So the solutions are in the book at the end of the chapter, and I'll come back on this in a minute. So learning outcomes, we'll learn about index properties of soil, how to classify soil, how to calculate effective stress, engineering properties, and then some simple geotechnical problems. If you have any kind of fun at following this introduction course, I highly recommend the second course in Geotechnical Engineering, which is Geotechnical Engineering Design, CVN 435. Because there we design foundation, slope stability, factor of safety, we design retaining walls. I mean, frankly, it's a lot more fun. I wish somehow we could invert the two so that you have the fun first and then you learn the basics afterwards. But unfortunately, it's difficult to build a building without the foundation sort of thing. Additional outcomes. So then you have a list of all the topics of the lectures with the date. And then the book sections that correspond to the lectures. And then you have the book problems. And that brings me to assignments. The assignments, and again this is mentioned in there somewhere. The assignments are optional. You don't have to do them. I highly recommend that you do them, because if you don't do the assignments, you're going to be in bad shape for the midterm and the final. So while they are optional, I certainly highly recommend that you do them. And as an incentive, I will give you 1% point bonus on the final grades. So once we average all your grades, the labs, the midterm, the final, I'll give you 1% bonus on the final grade for each one of the 5 optional assignments if it is submitted in time and if you have a grade of 90% or more on the assignment. Now, that shouldn't be very hard, because all the assignments are problems that are in the book, and therefore you have the solution. So take the time to do these assignments. Don't look at the solution at first. I mean, that would be, I know you can copy stuff, but take the time to do the assignments, and then if you get stuck, then you can look at the solution so that you make sure that you learn how to do those things. That was one of my frustrations when I was a student. I'd try, I couldn't find the answer, and then I was stuck because nobody could tell me what the answer was. So you have the solutions in there. 5 assignments, and so you'll have the column of the book problems and the assignment that corresponds to that. All right, so that's grading. So you have there's a midterm. Let's see, the midterm will be on 12 October. 12 October midterm, and then we'll do that by you doing it remotely and under time constraint. I'll explain more as we get closer to midterm. So there's a midterm on 12 October. There is a final examination, and we don't have the date yet because the registrar hasn't conveyed those dates for us, the final examination. But the last class is 23 November. All right. The midterm is 30%. The final is 40%. The lab reports and lab quizzes is 30%. So that's up to 100, plus the 1% point for each optional assignment that I mentioned. Attendance at all lab session is required, and let me talk a little bit about how we're going to do the lab. Right? So the lab will be offered in two ways, in person and online. Number one, the students must view the two pre-recorded lab videos. One is by Mike Linger, covering an introduction to the lab content and a demonstration of how to perform the test. And one is by your teaching assistant, covering how to reduce the data. This always takes place online. You got to watch those videos online before you come to the lab. So you have to view those videos and study them before you come to the lab. The lab starts on time, as noted in, depending on your section, and in the actual lab room for those who come in person. Now the lab can handle, because of distancing and all that, the lab can handle 12 students at a time. So that's smaller than the sections that are typically 17, 18, 19 students. So the way we're going to do this is the first 12 students on the roster of a section are invited to come in person for the first lab. So if you're one of the top 12 in that section, you come in person. You're invited to come in person. The teaching assistants will send an email to the students of a section to explain who those students are, to confirm. The remaining students, so if you have a section of 18, the first 12 come in person, the last 6 will have to do the first lab online. The lab is videotaped and placed online for those remaining students to follow it online. The following week, second lab, the students who were online the first week are invited to come in person in addition to the first students on the roster up to a total of 12. So let's say there were 18, the 6 that were online the first week have priority to come in person the second week, and then we add the top 6 in the roster to add up to 12, and then we rotate on that basis. So that way, all students get to do in-person labs, about 2 labs out of 3. And then as the semester progresses, the TAs will meet with the profs to optimize and adjust the system to make sure that it works well. Obviously, it's a new situation, and we're trying to optimize, so bear with us, and we will we'll make it work. All right. Let me talk a little bit about geology in general before I talk about examples of geotechnical engineering. And so let me go to page, so I'm on page 16. Page 16 of the book. And I would like to first talk about the Earth, our planet. So this is a big ball. The diameter is about 6,400 kilometers. So we're sitting on a planet. And this planet is 6,400 kilometers in radius. And the most popular scientific thinking is that the universe started about 15 billion years ago, and the Earth appeared 4.5 billion years ago. So about 10 billion years, there was no Earth. And the Earth formed, according to the same theory, when a cloud of interstellar matter coalesced and through gravity actually collected itself together 4.5 billion years ago. And at the time, it was very hot. And over those 4.5 billion years, the Earth has cooled down. It's still very hot in the center, about 5,500 degrees Celsius, so that's very hot. But it's quite cool on the outside, even though we're in Texas and we complain about, 100 degrees Fahrenheit, which is about 40 degrees Celsius, and we say, my goodness, that's hot. That's very cold, actually, compared to the center of the Earth. But, so the outside is cold, the center is still very hot. So it's cooling down from the outside in. And because the Earth is made of different materials, the center is essentially melted metals. So they have a density of 70 kilonewton per cubic meter, but the lighter material kind of floated to the surface, and that's rocks, okay, the silica based. Now, they were melted a long time ago, and they're cooling down, and as they cool down, they become hard. And so we're essentially sitting on a ball of fire. The outside shell, maybe 100 kilometers, is hard. So down to, if this is 6,400, you can see 100 kilometers here, all the way around, is rock plates. Okay, so this may be, let's say, 100 kilometers. But the center is still squishy. And through magnetic currents, the center is actually moving around. And the motion of this liquid, if you wish, in the center is actually disturbing that shell. It's cracking it, it's pushing it, and that's plate tectonics, and that's earthquakes. Unfortunately, the movement of these rock plates is sudden, it's not smooth, and so that's how we get earthquakes. And a long time ago, I remember talking to one of my colleagues and saying, I think earthquakes, we can solve this quite easily. All we got to do is pump up some Vaseline in the faults, and then it's going to be nice and smooth. Now, we can't stop the movement, but at least it won't be jagged and create some significant vibration. He said, Jean-Louis, it's a pretty good idea, except the first time where you inject the Vaseline, you might find California in Alaska. Okay, so that would be a bit of motion at the beginning, but anyway, seriously. So 100 kilometers on the outer, so we're sitting on an egg. We're literally walking on an egg. And to me, that conveys this important message that we have to be very, very careful about our planet. We have to care about the environment. We have to care about sustainability of all the engineering projects that we do, because it doesn't seem, when you look at it this way, it seems to be pretty fragile. Now, having said this, 100 kilometers of rock, that's still pretty strong stuff. Incidentally, the deepest hole, remember I said this is very hot. And some people come to me and say, we've got some real energy problems. I say, are you kidding me? We're sitting on a ball of fire, and you think we have energy problems? So geothermal energy, in my mind, is a fantastic source. It's clean as can be. The problem is, right now, it's expensive. And so we need to learn how to drill holes through this crust, 100 kilometers, into the hotter material, and then be able to generate energy out of this process. The deepest hole in the Earth's crust that's ever been drilled is 12 kilometers deep. The Russians did this up north. And when they reached 12 kilometers, they ran out of money, and so they stopped. But that's the deepest hole, 12 kilometers out of 100. So there's plenty of room to drill. incidentally, this 12 kilometers is about the same size as the thickness of the atmosphere that surrounds the Earth and really protects us from the sun rays and does a lot of good things for us. All right, so that's the Earth. So it's made of, as I said, silica-based materials on the outside, and they cool down because outside is cold, and it forms rocks. So the rocks are either igneous, sedimentary, and metamorphic. Okay, igneous is from the Latin fire, so it's rocks that came through the crust, through volcanoes, and then cooled down. Sedimentary is material that has been debris that existed on the surface, and they were re-cemented by either chemical action or other processes. And metamorphic is rocks that have been transformed by either temperature or very high pressures. Okay, so these are the types of rocks, but that's not what we're here to study, because typically rock is a much stronger material and we don't have as many problems with rocks as we have with soils. So geotechnical engineering, although it does include soils and rocks, we tend to focus on the soil part because that's where the larger problems are coming about. I mentioned one more thing on the Earth here. I mentioned that as you go deeper, so if I plot a temperature here, so this is temperature in degrees C. I said at the bottom here, you're at about, at the center, you're at about 5,500 degrees C. Because it cools from the outside in, it actually, the temperature increases quite rapidly and then slowly. This gradient here is about 15 degrees C per kilometer. So back to the Russians, when they drilled the 12-kilometer hole, 12 times 15, it was starting to be very hot, okay? So they had, these issues, not just the money issue, but the temperature was getting really hot at the bottom of the drill stem. All right, so these are the rocks. That's the planet. Concentrate in your life as a civil engineer on making sure that you take good care of the environment, take good care of design things that are sustainable, so that your children and their children have a chance to enjoy the planet for a lot longer. All right, geotechnical engineering. A little bit of a story on geotechnical engineering. My father was a civil engineer, and one day at the end of high school, he looked at me across the kitchen table and he said, "Jean-Louis, I shall be a civil engineer." I said, "Yes, Papa." So I didn't choose civil engineering. And then when I, at the end of that civil engineering school in Paris, when I went to Canada to study my master's degree, I went there because basically they were paying me. They were offering me a researcher citizenship. And I said, wow, this is fantastic. You're going to teach me something and you're going to give me some money to be able to study. That's fantastic. I'm coming. So I went there and I said, by the way, what am I studying? and they said, Geotechnical Engineering. I said, what the heck is that? And so I got told to be a civil engineer, and I got bought into being a geotechnical engineer. The good news is, if fast forward some 50 years, and I'm really still enjoying it. I think it's a remarkable field, because it's a tremendous balance between science and art and mathematics and judgment, and every project you deal with is new, because we didn't make the soil, and everywhere we go it varies quite a bit, and so if you ever think that you know everything about geotechnical engineering, just wait until tomorrow and you'll have a big surprise. Having said this, what is geotechnical engineering? Well, let's take a minute to write a possible definition. So geotechnical engineering is, I'll say, relatively young field of engineering, dedicated to, how did I write this? Dedicated to, so let's put dealing with the top. So engineering, I say relatively young, because geotechnical engineering is about 100 years old, 110, 120 maybe. So it's quite young compared to many other fields, even within civil engineering. So relatively young field of engineering, dealing with the soil, the top, I'll say the top 100 meters of the earth crust. So soil and rock. For the purpose of civil engineering structures. Okay, that's one definition. You know, people could argue with it, but some important things here. So we're civil engineers, and we're the folks that deal with what's under the ground. Not that deep, 100 meters, but not that shallow either. Agricultural engineer deal with the top meter. Geotechnical engineer deal with the top 100 meters. Petroleum engineer deal with the top 3, 4, 5 kilometers. So that's our domain, if you wish, 100 meters. So we have drill rig, and I'll explain in the next lecture how we actually take samples and study those samples to see how strong, weak, and their behavior. But that gives us essentially what it's all about. So if you deal with geotechnical engineering, then you have essentially you either deal with foundations, and these foundations can be shallow. So, for example, you might have a building, and this building has columns, and each one of those columns is on a spread footing. Also, a piece of concrete. This building is actually on spread footings, They're about 3 meters by 3 meters by about 1 meter thick. And the columns rest on these concrete footings that rest to the, on top of the soil. So there, the question that has to be answered is, one, what is the ultimate pressure, piece of U, that the soil can actually carry? And then the second question is, once you have the ultimate pressure and you put a factor of safety on that ultimate pressure, so you know, typically 2, 3 are typical factors that we apply on this ultimate pressure. Now we're going to load and resistance factor design, so it's a different story, but we have the ultimate pressure, we divide by a certain factor of safety to make sure we have a safe pressure under the footing here, safe pressure, P safe. But the second question is the settlement, S. In other words, even though you have a safe pressure, how much is this building going to settle? And there we say, well, we'd like this building to settle on this much, 20, 30 millimeters. Incidentally, I'm going to try my best to talk to you in the SI system. This unit business to me is important, and I realize that there are two sides to the story. But you know, hey, coming from Europe and going through Canada and now the United States, I've been exposed to both systems, and the problem is, if you have any desire to deal internationally, working with inches, pounds, and feet is going to be a killer. I mean, it's not going to be very easy for you to go to any other country and deal with it. So I'm going to teach in the SI system in hope that down the road everybody uses the SI system. And I understand that for a country to switch from a system to another system, it's very expensive and time consuming, but I really feel that it's important to, so anyway, so settlement of buildings typically 20 to 30 millimeters. Although we have structures like the Washington Monument, we'll talk about it, settled about 1 meter. The San Jacinto Monument, celebrating the 100-year anniversary of the freedom of Texas, settled about this much. Some of the buildings in Houston also have settled, but we tend to calculate, to design for this kind of a number. This can be debated. All right, so that's shallow foundations. The other type of foundations that we deal with is deep foundations. So deep foundations, if, for example, we calculate piece of U and it's very small, and so the footing has to be very large because the building weight divided by the area that has to be satisfying PSA, or if the settlement is quite large, then shallow foundations does not work, and we may have to use piles. So deep foundation, we call them piles. You have the same building like this, and you have the columns again, and then you still have to have a pile cap, which is basically the same as the footings, but now under the pile caps we're going to have to put some piles. So piles vary in diameter significantly. They can be as small as 0.3 meters, as large as 3-4 meters sometimes. But you calculate their capacity because there might be in here at some depth another layer that's quite a bit stronger. So this might be soft and this might be hard. And then here, we then say, well, we need to drive some piles, and we'll put some piles under those pile caps and transfer the load of the building to the hard layer through those, essentially those columns, if you wish, in the soil that we drive so that the weight of the building is transferred to the hard layer, and then we can satisfy the same two things. So we have to calculate here the ultimate resistance of the piles, and we also have to satisfy the settlement of those piles. So these are two aspects of geotechnical engineering. Another aspect of geotechnical engineering is slope stability. So let's say that you're in charge of an open pit mine, and you have the client is an energy company, and they have discovered that some 50 meters below the ground surface there is a body of coal or lignite right there, and let's say lignite, and they say we want to go and mine that lignite so that we can sell it. And you say, well, that's fine, we will, and the question is, how steep a slope can I dig with the slope being safe? And so the question here is, what is the angle beta of that slope such that this angle beta satisfies a certain factor of safety? And that's what a geotechnical engineer would do. And of course, the client, your client, the open pit mine company, or the energy company, wants this angle to be very steep. Because the steeper the angle, the less they have to excavate, the less time, the less money, and therefore the lignite that they get, they're going to be able to sell it and make a bigger profit. So they're pushing the geotechnical engineer to say, no, no, I want to put it straight down. And you say, no, it's not possible. The soil will collapse and you'll have a mess. So then they say, well, how steep can I go? 60 degrees to 30 degrees? And so that's our job as geotechnical engineer to find how this slope. And there are some other applications for slope stability. For example, if you have a large dam, so you have a river coming down and you want to build a large dam so that the water is going to be on this side, water on this side, and the dam has a certain core, and the question is here, how steep should this slope be and how steep should this slope be, because these dams are often made of soil. And you only have two types of dams. If the valley is fairly narrow, then we build arch dams. They're concrete dams, they're arched, and they bear against the mountain sides or the canyon sides, and they retain the water through this arching, typically made of concrete. The example, the Hoover Dam. The other solution, if the valley is quite large for that river, then the arch dam is not feasible, too expensive. And then we use earth dam. Earth dams just sit there by, they're heavy, the weight is what prevents them from sliding, and they retain the water pressure that's exerted behind them. due to the fact that they're heavy. And of course, in the earth dam, you got to make sure the water doesn't come underneath or through the dam, because this is soil, and soils are pervious. But the slope stability is another issue when it comes to geotechnical engineering. Another topic is retaining walls. So retaining walls, if you, for example, you have a side of a mountain like this, and the mountain is like that, and you want to make a cut in the mountain to put a road, then right here, you're going to have to build a retaining wall. And this retaining wall is going to have, and then probably here you have to put a guardrail so people don't fall in the ravine. And then behind that retaining wall, what the geotechnical engineer will have to do is calculate the pressure that is generated against that retaining wall, so that the retaining wall doesn't slide and doesn't overturn. And so there would be a resultant force, if you wish, here, P, that would have to be calculated by the geotechnical engineer. There are many different types of retaining structures. This is a structure that builds from the bottom up. But if you're in downtown Dallas, New York, and you want to actually put a new tunnel or a new water line, you have to dig a trench, and the trench is likely unstable, so you have to put the retaining wall on either side of the trench. So in this case, you might have, so that, let's say this is the street, you might drive some sheet piles in the ground, and then the cars maybe on this side here going in this direction. So you take half the street, and then you put your sheet pile, and then you excavate between the sheet piles, and as you go down, you place some anchors in the ground. So you anchor the retaining wall to be sure that it's going to be able to hold, and then so that you can come back in here and put maybe a subway line or whatever you're trying to place on the ground, and then you backfill, and then so these are top-down structures. This is a bottom-up structure. This is a top-down structure, both retaining structures. There's a new type of structure that's becoming very popular, and it was called reinforced earth, but now it's called mechanically stabilized earth walls, MSE walls. And you see them everywhere along the highway because they work very well, and they're less expensive than these types of walls. When you have to go, a typical highway wall is going to be 7 meters, and these types of walls, and I'll explain in a minute, are typically less expensive. They resist, they deform better, they resist earthquakes as well better than these rigid structures. The way these walls work is you place a layer of soil, and then on top of that layer of soil, you place a layer of reinforcement. steel, let's say. And then you place another layer of soil, and then a reinforcement, soil reinforcement, soil reinforcement, soil. And you can go up like this, 40, 50 meters. They're record heights. Okay? And then, as I said, you have reinforcement here at each level. So these MSE walls are to soils what reinforced concrete is to concrete. You know, reinforced concrete started around 1910 or so, when people started to say, hey, good idea, tension is not a good property of concrete, so let's stick some steel in there, because steel has a lot of tension resistance. And they started to do that. So that was 1910. This MSE wall concept started around 1960, 50 years later, when a fellow by the name of Henri Vidal, French guy, apparently the story goes that he was on the beach and he was placing some pebbles and a sheet of paper, pebbles, sheet of paper, pebbles, sheet of paper, and he was able to stack up the thing, and so he said, hey, that's a good idea, let's do this. And he went after it, he got organized, he did some tests, he patented the whole thing and became very rich, and he's dead. But he spent most of his time, of his life, defending his patent in a court of law. Because when you have something that's really smart and valuable, you're going to have to protect your invention fiercely. Because everybody's going to be after it to try to copy it. And a patent only lasts so much, typically 17 years for a patent. After this, anybody can copy it. But 17 years protection gives you a chance to really get going and establish your market. So very, very ingenious solution. Some of the other things I wanted to mention. So these are, if you wish, the core topics associated with geotechnical engineering, but there are others. For example, landfills. Landfills are, this is where we put our waste, and as you know, we generate, as human beings, a tremendous amount of waste. And so this waste has to be disposed of somewhere safe, and that's why we build landfills. So landfills are huge holes in the ground where we come and dump the waste. Well, you can't just, we used to do it that way, but now you don't do it that way. You can't just dig a hole and put a lot of bad stuff in the hole. So what we do is we put a liner. So right here, we're going to put a liner. And the purpose of this liner is going to be to protect the ground, because you may have, you may have groundwater down here somewhere, and you're drinking this. So you don't want, so, once you start piling the waste in here, and sometimes, the space is so valuable that these landfills are actually end up being mountains. And the landfills, so you don't want some of this, if it rains and it's coming down, you don't want all this to actually percolate through and pollute your source of drinking water, even though we treat it and make sure chemically that it's safe. So we actually put a liner on top of the landfill. We cap it so that we enclose this area. And this liner is made of geosynthetic, and clays. The idea is to make sure that the permeability of these liners is very low, so that very little water goes through it. And if it does, we have a way to collect this leachate. So below the liner, you would have a leachate collection system, so that you could pump this, what little went through the landfill, and then we can be sure that we don't have an intrusion. But that's the most recent way we do these things. And landfills have been around for dozens and dozens of years. And I can assure you that 100 years ago, we didn't have the kind of control that we have now for those landfills. Let's see, I believe that's, let me see if, I had made a list here. Oh, the last thing, I'll take 1 minute. The last thing is tunnels. Tunnels. And tunnels are getting more and more, the interest in tunnels is increasing because, you know, we're running out of space. You've seen all those very tall structures. And we're starting to think about making use of the underground. And so tunnels, like subway systems, developing, tunnels are becoming quite in high demand. And the issue with tunnels is mostly a construction issue. There's not that much design in terms of what the geotechnical engineer, it's critically important that the geotechnical engineer be involved, but the tunnel itself is more of a construction issue than it is a design issue, to make sure that, you know, the tunneling boring machine doesn't get stuck, make sure that the water doesn't come into the tunnel, make sure that you don't have, if you have structures in there and you dig a tunnel, or, you know, you have big settlement, that's not good, so you have to control those things. So basically, that's the world of geotechnical engineering. And next time we will start by talking about site investigation. If we have a project, how do we go to the site, what do we do at the site, and what kind of samples and numbers and tests do we run, okay? So I'll see you next time.